Let's talk about how to draw Lewis structures and how to draw resonance forms when resonance is involved. There are several steps we'll take in order to draw an accurate Lewis structure. The first thing we need to do is to draw a skeleton. This is going to show the connectivity of the atoms. How are they put together? And what we're showing here are the sigma bonds. These are the single bonds that connect the atoms. And of course, each atom must be connected by at least one bond to the overall structure. The next thing we want to do is count the total number of valence electrons brought in by each of the atoms. And what we want to keep in mind is that the number of valence electrons equals the group number for that atom. So with the use of the periodic table, it'll be pretty straightforward to figure out how many valence electrons are coming in. Next, we'll subtract the charge if it's a charged species. And finally, we're going to fill in the missing electrons. Now, the goal here in filling in the electrons is we want to fill in as many octets as possible. We're going to follow the octet rule, and we're going to get as many atoms to have 8 electrons around them as possible. Now, there's one thing we really want to keep track here when we're adding in our electrons is that we never will have more than 8 electrons on carbon or nitrogen or oxygen. Okay, those atoms along the second row of the periodic table have no way to expand and to accommodate any more than 8 electrons, so we have to make sure that we never have, for example, 5 bonds to any of those atoms or 4 bonds in a lone pair, anything that will ever total up to more than 8 electrons. Okay, and finally, we're going to look at the atoms involved in the Lewis structure and determine formal charges. If any are necessary, we'll take a look at those. If we see them, we'll draw a nice clear plus charge or minus charge. It's a real good idea to circle your charges so that they're very obvious to the observer and not to be mistaken as maybe an extraneous pencil mark on the page. Okay, so let's take a look at an example. Here we're given a condensed formula, and if we're asked to draw the Lewis structure, the first thing we'll do is we'll draw a skeleton. So we're going to show our connectivity. That chlorine is connected to the carbon. Okay, and these 2 hydrogens, each hydrogen can have only 1 bond, so one is attached, both are attached to the carbon, and then that carbon is attached to the next carbon, and finally that carbon is attached to a nitrogen. So there is the skeleton of the molecule. We've shown all the sigma bonds. And before we fill in the remainder of the electrons, we need to figure out how many electrons are going to be in the Lewis structure in total. So we'll do that by counting up the valence electrons. We have 1 chlorine. We have 2 carbons. We have 1 nitrogen. And we have 2 hydrogens. So with the use of the periodic table, we can see how many electrons each of these atoms brings in. Chlorine is in group 7, so it brings 7 electrons. Each carbon brings in 4 electrons for a total of 8. Nitrogen is in group 5, so that will bring 5 electrons. And each hydrogen brings along 2 electrons. And we're going to add these up, which will come to 22 total electrons. That means that in the end, our Lewis structure is going to contain 22 electrons as either single bonds or pi bonds or as lone pairs. Now, in drawing this skeleton, we've already used some electrons, right? Every single one of these sigma bonds represents 2 electrons. So we've already shown 2, 4, 6, 8, 10 electrons. So we can show that 10 electrons are already used. So we really have 12 electrons remaining to be filled in. So how are we going to decide where those electrons go? Well, we're going to try and fill as many octets as possible. So we'll start with this chlorine. This chlorine has just 2 electrons bonded to it, and so it wants a total of 8. So what we can do is we can add 3 lone pairs of electrons. So add another 6 electrons, and now this chlorine has a filled octet. This carbon has 2, 4, 6, 8 electrons, so that's a filled octet. Remember, hydrogen can only have 1 bond, so having just 2 electrons to a hydrogen fills its octet, if you will. It gives a filled valence shell. But this carbon has only 2 bonds, so 4 electrons. So we could think about adding these as lone pairs. And then we come to this nitrogen. We find this nitrogen also needs 6 electrons. So we can try adding lone pairs there as well. But we're going to find out suddenly that, we only had 12 electrons to add in. And so far we've added 2, 4, 6, 8, 10, 12. These are the only electrons we have to play around with. And in this Lewis structure, we haven't filled all of our octets. So a better strategy than just adding things as lone pairs is to think about sharing the electrons between 2 atoms, and that way you can count the electrons for both atoms. So for example, on this carbon, instead of showing this as a lone pair of electrons, we can share them as a pi bond between carbon and nitrogen. And in fact, we can do that with the second set of electron lone pair. So if we were to draw a triple bond between carbon and nitrogen, that gives this carbon 4 bonds for a total of 8 electrons, and also gives this nitrogen 8 electrons. 3 bonds and a lone pair, 2, 4, 6, 8. So this would be the best Lewis structure for this molecule. It has as many filled octets as possible. Turns out there's no formal charges in this molecule. Let's look at an example that would have a formal charge to see how we would handle that. So this next molecule, we could draw the backbone. If we wanted to draw the Lewis structure for this, we have a CH3, so that carbon has 3 hydrogens attached. And then it's attached to an oxygen, and that oxygen has 2 hydrogens. It doesn't matter the angles at which you draw these bonds. We're not trying to represent a 3-dimensional molecule here. We're just showing the connectivity, so don't get too worried about whether you draw this hydrogen up or down or to the side and so on. Okay, so there's our skeleton. Let's count up our valence electrons. We have 1 carbon, which brings 4 electrons. We have 1 oxygen, which brings 6 electrons. And we have 5 hydrogens, and that brings 5 electrons. So we have a total of 15 electrons, which should give us some concern because we have an odd number of electrons. That's not very typical in a stable organic molecule because typically electrons come in pairs, so it should be an even number. But what's happening here, the way we're going to adjust that is see that this has a charge. And remember when we looked at the rules for drawing a Lewis structure, we said that we're going to count up the valence electrons and then we're going to subtract the charge if necessary. So we're going to subtract that +1 charge, which means instead of 15, we're only going to have 14 electrons. Okay, does that make sense? Well, what the positive charge is telling us is that we are deficient an electron. We're missing an electron. That's why we have that positive charge. So instead of having the 15 that we normally would have for a neutral species, we only have 14. Okay, if this were negatively charged, that means we have an extra electron. So subtracting that charge means we would add an electron here. So make sure this process makes sense to you rather than just following some rules blindly. Okay, so we have 14 electrons to add to this Lewis structure. How many do we have in our structure already? 2, 4, 6, 8, 10, 12. We've already used 12 already, so there's only 2 electrons left to add to our structure. Where do they go? Well, there's only 1 atom that is missing its octet, so if we put a lone pair on this oxygen, we'll now have the best Lewis structure possible. The question now becomes, what do we do with this positive charge? Where do we put that? In general chemistry, very often we'll just kind of put a bracket around this whole thing and put a plus charge. But in organic chemistry, we don't want to use that formalism because it's going to be very important to us in organic reaction mechanisms exactly where the charges reside. So what we're going to do is we're going to determine the formal charge for each atom in the molecule. So let's talk about the process for determining formal charges. So this is something that's for each atom. One by one, we're going to inspect each atom and determine whether or not it should be charged. We're going to determine what's described as the electron count for that atom. Now, in a lot of textbooks, you'll see a kind of a complex calculation to be used for this formal charge, but it's really very simple, and we should avoid using an equation if we can. The electron count is simply counting up all the non-bonded electrons, in other words, all the lone pairs, and half of the bonded electrons. So that means we're just going to count 1 electron for each bond. And we're going to compare that electron count with the valence electrons. If we find that we're missing an electron, that means we have a plus charge. And if we find that we have an extra electron, that means we have a minus charge. So let's look at an example. Okay, so for example, let's look at carbon. How many valence electrons does carbon bring in with it when it bonds with other atoms? It brings in 4. Carbon wants 4 electrons to be stable and neutral. It still wants to have those 4 electrons. Let's take a look at the carbon that's in this Lewis structure. When we count up the electron count for this carbon, we're going to cut each of these covalent bonds in half and just see how many electrons are owned by that carbon. So we'll count 1, 2, 3, 4. And so for this carbon, we see that it wants 4, and it has 4 electrons. And so that means it is a neutral atom. There is no charge for that carbon. Now let's take a look at this oxygen. What is the valence for oxygen? Oxygen wants 6 electrons in order to be neutral. And what is the electron count for the oxygen in this Lewis structure? Well, we have 2 non-bonded electrons. Those are owned completely by oxygen, so we'll count those completely. 1, 2, and then half of all our bonded electrons. 3, 4, 5. Oxygen has 1, 2, 3, 4, 5 electrons. So it wants 6, but it has 5 electrons. That means that oxygen is missing an electron. It's 1 electron short, and if you're missing an electron, you're going to have a +1 charge. So where do we locate this positive charge in the molecule? We're going to put it right here on oxygen. Doesn't matter where you put it, top, right, bottom, left, somewhere very close to the oxygen atom, indicating that in this molecule it's the oxygen that is the most electron deficient and has a +1 formal charge. So let's take a look at some typical stable bonding patterns that you should really know by inspection the more practice you have with Lewis structures. So for example, if we're taking a look at a hydrogen atom, what does a hydrogen atom usually look like when it's in a molecule? Well, it's going to have just a single bond. There's going to be 1 bond and 0 lone pairs. When you have that bonding arrangement, the electron count for that hydrogen, we're going to cut that bond in half. That electron count is just going to be 1, and because this equals the valence, that would indicate we have a neutral hydrogen atom. So any hydrogen that you attach to your Lewis structure by a single bond, you automatically know is going to be neutral, and you don't even have to bother checking its formal charge. How about a carbon? What does a carbon typically look like to be neutral? Well, a neutral carbon will have 4 bonds, maybe 4 single bonds, or combinations of triple bonds or double bonds. But if we have 4 bonds and 0 lone pairs, then the electron count for that carbon will be 1, 2, 3, 4, which equals the valence for that carbon. And so any carbon with 4 bonds we know will be a neutral carbon, just by inspection. How about a nitrogen? We just saw an example of a nitrogen, and that example is pretty typical of a neutral nitrogen. If we have a nitrogen with 3 bonds and 1 lone pair, that will be a neutral nitrogen. Let's check the electron count to verify that. That will have 1, 2, 3, 4, 5 electrons for its electron count, which is the same as the valence for nitrogen. So any nitrogen with 3 bonds and 1 lone pair will be neutral. And how about oxygen, like the oxygen in water? What we have are 2 bonds and 2 lone pairs. So we want 2 bonds and 2 lone pairs because that will give us 1, 2, 3, 4, 5, 6. That'll give us 6 electrons for our electron count, which is equal to oxygen's valence. And finally, if we take a look at a halogen, we'll represent a halogen with the letter X very frequently in organic chemistry. So something like fluorine, chlorine, bromine, iodine. How does that typically bond in a molecule in a Lewis structure? Typically, we'll have just 1 bond and 3 lone pairs, just like the chlorine we saw on our recent example. 1 bond and 3 lone pairs is a very stable looking halide because it has 2, 4, 6, 7 electrons around it, and that's exactly what it wants according to its valence. So just by a quick inspection, if we see this normal typical bonding pattern for any of these commonly encountered atoms, we know that it's going to be a neutral atom. And more importantly, if we see something that deviates from this normal pattern, we're alerted to the fact that there's going to be a formal charge, and then we need to do our formal charge determination so that we can properly locate them. So let's see another example. How about the Lewis structure for nitric acid, HNO3? Well, HNO3 is very often the way we draw nitric acid, but a better shorthand or condensed notation would be HONO2. That better represents the actual connectivity of the atoms. And when we go to draw the skeleton for this, we might think that we do HONO. Now that would be a possibility for HONO2, but it gives us an arrangement where two oxygens are bound directly to one another. This is called a peroxide. This group is called a peroxide, and this is really quite unstable, explosively so, in fact. And so this is unusual. So while it might be possible that your structure is going to be a peroxide, we're going to look for an arrangement of atoms that avoids that unstable connectivity. And so instead, the Lewis structure, the correct connectivity, has all three oxygens bonded to the central nitrogen. So that's actually the connectivity for nitric acid. Okay, we can go ahead and add up our valence electrons. Now, as we get more practice with this, we'll eventually be able to skip this step and just try and fill in our Lewis structure by inspection, trying to give everyone an octet. But let's try this one more time. Our hydrogen brings 1 electron. Our nitrogen brings 5. And our oxygens each have 3, so that gives us 18. So we have 24 electrons total that will be in this system. And we've already shown 2, 4, 6, 8 electrons. So that means we have 16 electrons left to distribute on this structure to try and fill as many octets as possible. So right here I see this oxygen. I know oxygen likes to have 2 bonds and 2 lone pairs. So that would be a good idea, is add 2 lone pairs right here. And we could do that for this oxygen as well. We can have 2 bonds and 2 lone pairs to that oxygen. So that would give a good looking oxygen. This nitrogen now has a filled octet. It has 4 bonds for a total of 8. And so our remaining 6 electrons can go on this oxygen to fill its octet. So we've added 2, 4, 6, 8, 10, 12, 14, 16. So we now have a total of 24 electrons. It's a good idea to check at the very end to make sure you have the correct number of electrons that you were expecting, because a lot of times when we're shuffling around electrons or moving them around, it's very easy to maybe add an extra pair or lose a pair of electrons, and then you have no chance of getting the proper Lewis structure. So this would be a Lewis structure for nitric acid, except when we take a look at it, we see that we have a few atoms with atypical bonding patterns. For example, this nitrogen has 4 bonds, and usually we like to see a nitrogen with 3 bonds and a lone pair, so we need to calculate the formal charge for that. So nitrogen wants 5 electrons. That's its valence, but how many does it have when we calculate the electron count? For the electron count, we count 1 electron for each bond. 1, 2, 3, 4. So it only has 4. What do we do when we have a missing electron? That's a plus charge. So this nitrogen, every nitrogen with 4 bonds is going to be a positively charged nitrogen. Where do we have another atom that has an unusual bonding pattern? This oxygen. Instead of having 2 bonds, 2 lone pairs, it has something different. So let's count this. Let's remind ourselves, oxygen wants 6. And what does it have here? 1, 2, 3, 4, 5, 6, 7. This oxygen has 7 electrons. So here we have a case where there's an extra electron. And what charge would you associate with an extra electron? A negative charge. So any oxygen with 1 bond and 3 lone pairs is going to be an O-. So this Lewis structure overall is a neutral structure, just like the formula told us. There's no net charge, but it does in fact have formal charges within the structure. So that's why it's very important to recognize unusual bonding within a Lewis structure so that you can be alert to finding these formal charges where they exist. Now, there might be another Lewis structure that you could come up with for nitric acid that is equally good. How about instead of having the double bond to this top oxygen, we did the double bond to this bottom oxygen? If we did that arrangement and we filled in our lone pairs, it would still give us an N plus and an O minus, and this would be a second Lewis structure. When we have two Lewis structures that we can draw for a molecule, that means both Lewis structures are valid, and we call this relationship of having more than one Lewis structure, we call this resonance. Resonance means we have more than one Lewis structure that we can draw, and we're going to talk a little bit more about resonance in just a second. Let me show you one other possible Lewis structure that you might be considering. Now, what's very nice about this Lewis structure is it gets rid of all of our formal charges, right? So that is very tempting, isn't it? But there's a problem with it. This Lewis structure is impossible. What rule have I violated here? That nitrogen has 5 bonds for a total of 8 electrons. Because he has more than 8 electrons, I violated the octet rule, and this is impossible. Okay, so there are, in fact, 2 good Lewis structures that I can draw, valid Lewis structures I can draw for nitric acid, and these do represent resonance. So let's talk a little bit more about resonance and what that means. So as we just saw with nitric acid, resonance means that more than one Lewis structure can be drawn. And when we compare those Lewis structures, what we see is we have movement or delocalization of pi electrons and non-bonded electrons in p orbitals. We'll see that these are in p orbitals when we look at some further examples of resonance. And so one thing we're pointing out here is we're not moving sigma bonds. We're only moving pi bonds and lone pairs. The sigma bonds are staying the same. And the actual structure is a hybrid. So the fact that we can draw more than one Lewis structure for a given compound means that neither Lewis structure is an accurate representation of what the molecule really looks like. So what we do is we just try and draw as many Lewis structures as possible to show what characteristics the actual structure has. The actual structure is described as a hybrid, and so for nitric acid, the hybrid looks something like this. Remember, we had either a double bond to one oxygen or a negative charge to one oxygen. The hybrid has a partial double bond spread out to both oxygens and a partial minus on both and a plus charge on the nitrogen. So this is the actual hybrid. This is what the structure really looks like, but it's very difficult to work with a hybrid structure like this. So instead, we just draw a discrete Lewis structure and work from there, recognizing that discrete Lewis structure is not a complete story. Okay, so what we're saying is we're not flipping back and forth between structures. It is not an equilibrium between one Lewis structure and the other. Instead, it's called resonance, and we use this special arrow, which has a line with an arrow on each end, indicates resonance, and it means that we have this special movement of just our pi electrons and our non-bonded electrons. Now, it turns out that all resonance forms may not contribute equally. So although we might have 2 or 3 or even 4 resonance forms or even more, not all of them are equally good resonance forms, equally stable resonance forms, and so they don't all contribute equally necessarily. And we'll take a look at that on the next slide. Very commonly, we use curved arrows to show the electron movement from one resonance form to the next. We usually start with the first resonance form and show arrows on how we would convert it to the next resonance form and so on, so we only go from left to right. We'll see an example of that on the next slide as well. And remember, because we're not moving our sigma bonds, no atoms are moving. There's no change in the bond length, no change in the bond angles. Our atoms are fixed in space. It's just the lone pairs and the pi electrons that are shifting around, delocalizing in a continuous set of p orbitals. No sigma bonds break, we already mentioned that. And then there's also going to be no change in overall charge because we're not adding electrons, we're not removing electrons. The net charge has to remain the same. But of course, as we relocate electrons throughout the structure, our formal charges between atoms are most definitely going to be changing. The key thing that we need to keep in mind is that resonance equals stability. It's going to be very important to recognize resonance and be able to draw resonance forms and evaluate resonance forms, because when we find resonance occurring, that means we're delocalizing our electrons, spreading out electrons, and that's always a good thing. That always means we are stabilized by resonance, or we are resonance stabilized. So how can we identify when resonance is going to be happening? Actually, first let's discuss the stability of various resonance forms and how we would estimate which form is more stable. Here's an example of a molecule that has two different resonance forms. Which of these is more stable and which contributes more to the overall hybrid? Well, what we'll find is that the greater number of covalent bonds, the greater the stability, because more atoms will have complete octets. So the number one thing we're always going to be looking for to evaluate a Lewis structure is the more we have for complete octets, the better the Lewis structure. That's always our first thing we want to take a look at. So when we compare these two structures, we see that this carbon is missing an octet, while in the second structure, every atom has a complete octet, a total of 8 electrons around it. So this is the more important, this is more stable. We also say, we describe it as being a better contributor. So what does the actual hybrid look like? The actual hybrid looks more like this structure on the right because it is the more stable structure, is the better contributor. It's more important. It's more important than the first. Important. Because this is missing an octet, this is less important. Okay, and finally, let's see if we can use curved arrows to get some practice shifting electrons around. How would you say what's changed in going from this structure on the left to the structure on the right? Looks like this lone pair of electrons that used to be on oxygen is now being shared between the oxygen and the carbon as a pi bond. So what we do is we use an arrow, a curved arrow, showing these two electrons picking up and moving to be between the oxygen and the carbon. So this is a really good habit to get into so we can keep track of our electrons. Really important for bookkeeping for electrons when we do curved arrows. Okay, another thing to look for is if we have a separation of charge, if we can avoid formal charges, that would be a very good Lewis structure. So that's something to keep in mind. So if we compare this first structure to this next structure, those are both valid Lewis structures, but this is going to be the most important because this one has formal charges. And how about comparing this second one to the third one? Which of those is more important? They both have formal charges. And you might think about bringing that plus and minus closer together. That would be a good thing, except something else is missing in this last structure that makes it not as good as the middle structure. Looks like we have, with this carbon again, a carbon with just 3 bonds. This is missing an octet. So this is the least important because octets are the most significant thing that we're going to be looking for. And again, covalent bonds are something you can look for. I lost a covalent bond in this structure, so that tips me off to the fact that I must be have lost an octet. Let's do some curved arrow practice and going from this first to second structure. How do we convert that? This lone pair moved in to be a pi bond, and then this pi bond moved up to be a lone pair. Notice our formal charges have been created as a result. You can practice with those, double check those charges are right. And how about going from this second structure to the third structure? We've taken this pi bond and picked it up and moved it to be a lone pair on nitrogen. So we're moving pi bonds and we're moving lone pairs to do this resonance. Okay? Our third rule is that all other things being equal, a structure with a negative charge on the more electronegative element will be more stable. And similarly, if we have a positive charge that we're delocalizing, positive charges on the least electronegative atom will be more stable. So for example, when we look at this carbonyl, a CO double bond is called a carbonyl, we can pick this lone pair up and move it to the oxygen to give a C plus and an O minus. Or we could pick this lone pair, this pi bond up and move it to the carbon to give a C minus and an O plus. Now one of these resonance delocalizations is quite significant and the other is very unlikely. And because oxygen is more electronegative than carbon, the oxygen prefers to have a negative charge, better handles the negative charge. So this is important resonance. And this resonance is unlikely. And then finally, resonance forms that are equivalent have no difference in stability and contribute equally. So sometimes we might compare two resonance forms and not find any significant difference in their structure. For example, this guy is known as the allyl carbocation, and they both have one double bond and one carbon missing an octet, double bond, carbon missing an octet, and so because they have equal features of stability, they're going to be equal in energy and therefore contribute equally to the resonance hybrid. Okay, let's show our curved arrows. Looks like this pi bond is picked up and just jumped over to be on the other side, and as a result this positive charge will now be on the end carbon. Notice that with my arrows I'm never moving the charges. Our curved arrows only move electrons, so they're either going to start at a lone pair or they're going to start at a pi bond, and the charges will move as a result. So we'll just calculate those charges on the new Lewis structure. Okay, how will we know when to expect resonance delocalization, resonance stabilization? Well, there's three main structural features that we can look for. One possibility is to have an arrangement like this where we have a lone pair that is next to a pi bond. So the lone pair isn't on the same carbon as the pi bond, it's the next carbon over. We call this being allylic. So if we have an allylic lone pair, that tells us that resonance can occur. And the resonance that happens is as follows. The lone pair becomes a pi bond. And the resonance can't be done yet because if all we did was share this as a bond, this carbon would now have 5 bonds to it, and that would be impossible. So what happens is as this lone pair comes in to be a pi bond, this pi bond picks up and becomes a lone pair. So we use those 2 arrows. And what do we get as a result? We now have a double bond to the left-hand carbon. I had drawn this as an HC. We want to make sure that our atoms aren't moving. And single bond now with a lone pair on this carbon. Now, as a result, I think our formal charge has also moved. Let's take a look at that. What is the formal charge on this carbon? Carbon wants 4. It has 1, 2, 3, 4, 5. Carbon has 5, but only wants 4. So it has an extra electron. So this is where our negative charge is. So this is called allylic type resonance. And we have that every time there's a lone pair next to a pi bond. We'll look for that. Okay, here's another possibility. Now we have a vacancy next to a pi bond. We have an atom that's missing an octet. This carbon has only 6 electrons around it. And when that's next to a pi bond, again, we call that allylic. So this is an example, in this case, of an allylic carbocation. A carbon with a positive charge is called a carbocation. And what we have in this vacancy is we have an empty p orbital. A carbocation has an empty p orbital here, so it can interact with these 2 electrons in the p orbital right here. And what can happen is the pi bond can move over and fill that vacancy. This carbon now has just 3 bonds. We took a bond away from it. So that's where our carbocation is. It has 1, 2, 3 electrons. It only has 3 electrons, but carbon wants 4. So it's missing an electron. Okay, so we could have a vacancy next to a pi bond, like an allylic carbocation. And one last thing to look for is having a pi bond between two different atoms, such as in a carbonyl. We call this carbonyl-like resonance. It's called a carbonyl when you have a CO double bond. Okay, and every time we have something that looks like a carbonyl, we're going to pick up that pi bond. The electrons are going to move to the more electronegative atom. So we can pick up these two electrons and move them up to oxygen. So there's just a single bond, and instead of just 2 lone pairs, now there's 3 lone pairs on that oxygen. See how those arrows help us keep track of our electrons? Really good habit to get into. And let's take a look at our formal charges. This carbon has just 1, 2, 3 electrons. It wants 4. So it's missing an electron. This is a C+. And this oxygen has 1, 2, 3, 4, 5, 6, 7. Oxygen has 7, but it only wants 6. So this is an O-. So that would be carbonyl-like resonance. Okay, now these are 3 patterns to look for in molecules to anticipate resonance. There's another kind of resonance that exists, and this is something that we'll talk about a bit down the road. And it's looking at molecules such as benzene. Benzene is the molecule that has a 6-membered ring with 3 alternating pi bonds. We call these conjugated pi bonds because they're alternating. We have double bond, single bond, double bond, single bond. And when you have 3 conjugated pi bonds in a 6-membered ring, it's a very special molecule, and it has something known as aromatic resonance. It is an example of an aromatic compound. So there are compounds related to benzene that have the same special stability. And what happens in benzene is you can take these pi bonds and move them around the ring. This could shift over here, which causes this one to shift, which causes this one to shift, and you could draw the same molecule but with the pi bonds located in different positions. Now, does this look like it's resonance? Sure, we've kept all the atoms in their same position. We've simply moved around the pi electrons, and this is actually excellent resonance because since both of these are equivalent resonance forms, they contribute equally to the overall picture, and that really gives great resonance stabilization. So we'll talk a lot about aromatic compounds in the future. So let's try an example where we are asked to draw resonance forms and then rank them in terms of their contribution. So I've given here, just as our starting compound, a skeleton of a molecule. Let's see if we can fill in our lone pairs and pi bonds to give everyone a filled octet. This oxygen has 2 bonds, so let's put 2 lone pairs. That will make that oxygen neutral. This oxygen wants 2 bonds and 2 lone pairs as well, so we can make a pi bond here. And that also satisfies this carbon, because now this carbon has 4 bonds. I know carbon likes to have 4 bonds. And how about this nitrogen? Has 3 bonds right now. And if I added a lone pair, then this would be a neutral nitrogen as well. So this is an example of a Lewis structure that it's easy to complete just by inspection. It's possible to fill the octet for every atom and have them be neutral. So this in fact is a good Lewis structure for this. Now, are there any resonance forms? What we need to do is we need to look for patterns in this molecule that would give rise to resonance. For example, and there's several. For example, one thing I see is that I have a carbonyl. And anytime I have a carbonyl, I have carbonyl-like resonance where that lone pair, that pi bond can move up and become a lone pair. All carbonyls are resonance stabilized. And so that means that this structure also has, contributing to it, an O-C+ structure. Okay, so this is a second resonance form. What other possibilities are there? Well, I have a vacancy now. I have a carbocation that's missing an octet. Is there any way I can fill in that octet? Perhaps I can use some of these neighboring lone pairs. If I use one of these lone pairs, it brings me back to the Lewis structure I already have. But if I shared one of these lone pairs, that would give me a new Lewis structure. So I still have an O- up here. And this carbon now has 4 bonds, so it's neutral. But how about this oxygen? That doesn't look like a typical oxygen. Let's count. 1, 2, 3, 4, 5. This oxygen has 5, but it wants 6. So it's missing an electron. So this is where our plus charge has moved to. Now remember, this molecule started out neutral, so every Lewis structure, every resonance form from here on out has to have a 0 net charge, and this still does. We have a plus and a minus. Okay, there's actually one additional resonance form we can draw, one other Lewis structure that's possible for this. Do you see any other patterns that we haven't accounted for yet? How about having a lone pair that's next to a pi bond? This lone pair is allylic. Every time we have an allylic lone pair, that can be resonance where the lone pair comes in and the pi bond moves over. And that would give this structure with an O minus up top. And where is our positive charge now? Our positive charge is on this nitrogen, 1, 2, 3, 4. Nitrogen wants 5. And this is a fourth resonance form. Any other attempts at shifting around the lone pairs and the pi bonds will bring us back to one of these original structures that we drew. So these are all the possible resonance forms. Now let's rank those resonance forms and decide who is the best contributor and the worst contributor and so on. Of all these, I think this first one looks the best because it has no separation of charge, no formal charges. This is number 1. This is the best because it has no charges. It has filled octets. I should write that first, actually. And it has no charges. So this would be our best Lewis structure. This is the Lewis structure we would typically draw, and this is the one that best represents the hybrid. Okay, but these other Lewis structures also exist, and so that means they are also contributing to some extent to the rest of the structure, to the actual hybrid. Okay, so between these remaining 3, there's one that also stands out. Remember, the most important thing we should look for in Lewis structures is to have filled octets. And in one of these structures, we are missing an octet. Can you see it? Right here, this carbon has only 3 bonds, and so it does not have 8 total electrons. So this is going to be our worst because it is missing an octet on carbon, if you're missing where that is. Okay, these last 2 structures have completely filled octets, so let's see what the difference is between them. They both have an O minus, so that's the same, but here we have an N plus and here we have an O plus. So now we take a look at the location of those formal charges and decide where a positive charge would rather be. Which do you think is more stable, having an O plus or an N plus? Well, we know that oxygen is more electronegative than nitrogen. Oxygen is the second most electronegative atom in the periodic table, so he's more electronegative than everyone except for fluorine. So because he's so electronegative, would he like to have a positive charge? I don't think so. So it's better to have a positive charge on nitrogen. So this is going to be our number 2 structure, and this is going to be our number 3 structure. And when we compare these two, they have filled octets. Okay, but the N plus is better than O plus, and that's because nitrogen is more electropositive. Or you could say that nitrogen is less electronegative. That says the same thing. So in a case like this, we want to look for the differences in our Lewis structures, always looking for filled octets first, and then finding formal charges and trying to locate them on the best atom, depending on whether we're looking at a positive charge or a negative charge. So this concludes drawing Lewis structures and ranking resonance forms.